Okay, so I'm going to show you some programs, and I only got half an hour, so let's go ahead and dive into it. I'm going to be using Scheme, and let's begin by just concatenating two lists in Scheme. So we can use the built-in append. I'm going to append a list ABC to a list DE, and I should get back what? A, B, C, D, E, that's right. I knew you were smart. Okay. So that's append, great. And let's define append. I'm actually not going to define append. I'm going to define my append, just so I don't trash the built-in one. But so let's define my append. And in Scheme, if you don't know Scheme, that's fine. It's not much to it. We've got define that gives a name to something. So we're giving the name my append to a function we're defining using lambda. And this function is going to take two arguments, L and S. And we're going to have an if expression. So we're going to say that if L is null, that means L is the empty list, then what should we return? S. Okay, great. Otherwise, what should we do? Okay, so we're gonna do a my append. We're gonna do a recursion on, well, we ask a question about L, so we're gonna have to do something to L to make it closer to the base case. We didn't ask a question about S, so we can leave that the same. And we want L to be smaller, so we're gonna take the cdr of L, that's basically the rest of the list L. And then, as Byrd will point out, we want to cons on to the recursion. So we're gonna cons on the car of L. It's the first thing in L. And that's our definition of my append in Scheme. Okay, so let me just make sure my append actually works. Okay, my append works, great. All right, now let's define a slightly different version of append. And this is a version of append in a language called miniKanren, which is a language for relational programming. And we'll see what that means in a second through demonstration. But miniKanren is a language you can embed in other languages. Right now we're embedding it in a host language of Scheme, but we can embed it in Racket, Clojure, Haskell, Java, all sorts of languages. But we're going to use Scheme right now. We're going to define something, instead of calling it append, what should we call it? Appendo! Yeah, that's the right answer. Okay, so in miniKanren we have this tradition of ending names in O, and you can blame Dan Friedman for that if you know who he is. But Dan thinks that a little O kind of looks like a question mark for some reason. And that's why we have this O at the end. But so let's define appendo. That's a real story. Okay. Define appendo. And we're going to also have, appendo will be a function, just like append. And it's going to be a function of, well, we have the list L and S, but we're going to take another argument. We're going to take another argument, and I'll call this out, which is a little naughty thing to do, but I'm going to do it anyway. And I'm not going to explain to you exactly how the miniKanren code works. It's not really material for this talk. I gave a workshop on it this morning. But anyway, so I'm going to unify L, the empty list. That's equivalent to this null test. If that's the case, my out is going to be S. This might look a little weird to you. That's fine. It is a little weird. We'll do something about that in a minute. Okay, in this case, the recursive case, we want to break up the list L into cons of A and D. And this looks pretty obvious, right? And we're going to append. We're going to recur on D and S to get a temporary result S, or res. And then we're going to unify out with consing A onto res, and I believe this actually works. Let's see. So we're going to, I told you it's simple. So we're going to append ABC to DE, and now because our appendo takes 3 arguments instead of 2, we're going to go ahead and feed in an extra argument, and that's going to be this Q thing, which is really like a query variable. So you can think of this a little bit like a database query, except that our tables happen to be infinitely large. And so the Q is, you could think of it as sort of the output that you would get if you just called the regular append or my append in Scheme. So we should expect to see ABC DE associated with Q, and let's see if that actually works. Hey, it works, cool. And you'll notice that we have our answer in a list. Okay, we have a list, A, B, C, D, E, inside of a list. And that's because in miniKanren we can get more than one answer back. Okay, right now we're only getting one answer back. We can ask for more than one answer, so we can do a run 2. We still only get that one answer back. And we can ask for all the answers that are possible with run star. So give me everything. Once again, we only have the one answer. All right. So what's the point of this? Well, it seems a little weird to write append this way, right? So there must be something to it. Well, the cool thing here is that because we have defined our appendo as a relation instead of a function, we can think of appending or concatenation as basically a list of tuples or triples that involve 3 arguments instead of a function of 2 arguments to 1 output argument. So for example, this information should be consistent. We're saying if we append ABC to DE, we should get back ABCDE metaphorically. So that should be consistent. And when we run this, it should succeed. Okay, we should succeed. And the query variable Q isn't associated with this computation at all. So we're going to get some representation that Q, the value of Q doesn't matter. This is going to hold no matter what Q is. And we can see that because we have this underscore 0. That's our representation of the query variable when the query variable isn't involved in the computation, doesn't become bound to anything. Okay, so we can check things. We can also, by the way, check to see if something that's inconsistent is actually consistent. So ABCE is the output. That's not going to be consistent. So we should fail, and we get back the empty list. Okay? All right, so that means that's inconsistent information. All right, what else can we do? Well, we've got this query variable. We could put the query variable in different places. Okay? So let's put the query variable here, for example. All right, so what should be the answer for this query? Well, we have Q in the middle. List DE. All right, cool. So we list DE, and we can ask for more answers. We can ask for all the answers, and that's the only one. Okay, cool. All right, what else could we do you think? What else would be? Add another variable. That's a good idea. I like that. Okay, so how about we have like X and Y? All right, so where should we put these variables? Now we put them in the beginning, right? So X and Y. And we'll just ask for one answer to begin with. So here we're seeing a pair of lists corresponding to X and Y. When we concatenate those together, we should get ABCDE. So we're concatenating the empty list to the list ABCDE. Sure enough, we get ABCDE. All right. Let's go for a second answer. And we can see, sure enough, now we have the first list being the list containing A. And we can ask for all these things. And if you've seen Prolog or other logic programming languages, you probably have seen something very similar to this. Okay. So the interesting thing here is we're treating append as a relation instead of a function, and we can get all the values back, okay? We can play all sorts of other games. So for example, maybe I could do XYZ and put a Z here. So what happens if I run this query? That's not funny. My fans will turn on. I'm not even going to do it, because I'm going to crash something, I know. So, well, we could ask for like 10 of these, right? Okay. And, well, okay, I'll ask for like one of them. How's that? Okay, so here we're saying if we append the empty list to anything, then we get back that second thing, okay? And notice that we're not being particular about what that second thing is. In fact, it doesn't even have to be a list, because in Scheme, append, second argument, doesn't actually have to be a list. So we can append ABC onto 5. Oh, that's very classy, right? So anyway, miniKanren works the same way. Okay, so that's appendo, and this should give you hopefully some idea of what it's like when we go from a functional viewpoint to a relational viewpoint. Instead of looking at append as a function of 2 arguments, 2 lists, with an output of a list, we're looking at a relation of 3 lists, okay? And we could do this with numbers and with arithmetic, with multiplication, addition, things like that. In Prolog and other logic programming systems, this tends to be about as far as you get with the pure relational paradigm. Okay? Once you start getting more complicated programs, people tend to start using basically impure or extra logical or non-logical features, like if you use prolog, there's cut, assert, retract, there's a bunch of other operators to try to make things more efficient, to express negation and so forth, okay? What we're going to try to do is try to stay pure to the paradigm and try to see how far that can take us. In particular, what we're going to play with are interpreters for programming languages, Turing-complete programming languages, where the interpreter is written as a relation, okay, or the evaluator. So in Scheme, I have this read eval print loop, right? So I can just type in stuff like +34, right, and it evaluates and gives me a value back. So basically, we're going to play with an evaluator just like this, okay? But it's already written for us in miniKanren. I'm not going to explain how it's written. That was sort of this morning's talk, but if people are interested in it, I'm happy to tell you more about the details. But let's just assume we have this evaluator, and it's called evalo, okay? What a shock. And evalo can take an expression from a subset of Scheme and evaluate it. So let's try something here. So first of all, in Scheme, we have things like lambda xx. So we have a lambda expression. What does a lambda expression evaluate to in Scheme or Lisp? Any idea? A function, a procedure, right? So here, sure enough, we get a procedure. And this is the identity procedure. So if we apply this procedure to some value like 5, we get 5 back, okay? So let's try doing something like that with our evalo. So we're going to evaluate lambda xx. And now we have a two-place relation. So we have an expression we're evaluating. We actually have an environment, too. In this case, we're starting out with the empty environment. And we have the output value. So let's see what we get. Oh, yeah. You think I've learned after a dozen years. But okay, let's try this. Thank you. This is much better. Okay, so here's a closure. We're getting back a tag closure. And we have that closure has the empty environment. And let's try applying this function to a value. I don't know if we have numbers or not. Let's see. Yay, we do. Great. All right. So we can do things like apply the identity function to 5 and get back 5. Great. All right. Now, what can we do now that we're in a relational world? What would be fun to play with? Soon. Okay. All right. Well, let's put the query variable somewhere else, right? So if we go back to the previous query, so we have lambda xx, that's the identity function, and that's going to give us a closure. That's a representation of a procedure. That's the identity function, right? So what we could do, we could say, well, the output value is this closure thing, right? And we want to know what is a Scheme expression that evaluates to lambda xx. So what is a Scheme expression that evaluates to lambda xx? I mean, sorry, the closure, right? Well, you can see the answer, right? We already know it. So it's lambda xx is one answer, right? Well, we could ask for a second one, right? And here, we're using a pattern matcher. Okay, we can ask for like 10 answers, and we're getting all sorts of things. So here's like, this kind of a goofy answer. So this is, this is lambda nil, a procedure of no arguments. It returns, evaluates lambda xx when you call it, and it's being called with no arguments. And sure enough, that actually gives you back the procedure in Scheme, which is the identity procedure. Okay. All right, so we can kind of run things backwards and things like that. All right, so what else can we do? So Matt Might, who I'm working his lab in University of Utah, he's got this nice blog post on 99 ways to say I love you in Racket. This is like a Valentine's Day post, right? So he's got all of these little programs. And, well, gee, what do you think we can do here? So, all right, help me out. How do we do this? Yeah, I wouldn't do a run star. We could do, okay, if we want to do 99 ways to say, you want to show up, Matt, and do a run 100? Okay, fine. Take that, Matt. Okay, now what? List I love you. Okay, cool. That's the hard part. Segment. Okay, so let's see what we get. All right, so maybe this works. So let me just grab one of these things. We got some side conditions. We'll forget that. Hey, that works. Yeah, so you can play. I mean, you can do this. You can have 1 million of these. I actually do. In fact, I've been playing around with like training a recurrent neural net on these answers. When you have 1 million of them, you get a lot of data. You can kind of do fun stuff when you have this. Okay, so that's a fun thing we can do. What else can we do? All right, Buddha already said it. So does everyone know what a quine is? A quine is a program that evaluates to itself. And this is like a traditional hacker challenge, right? Is to do that. So how could we generate a program that evaluates to itself using this interpreter? Evaluate QQ. Oh, wow. All right. I'm expecting some grand quine here, right? Oh, what is that? It's saying _0 or _0 is a number. So that'd be like 5. 5 is a quine. Is 5 a quine? Yeah. All right. Woohoo! It's like very, very impressive. All right. Surely the second answer will be more impressive. #T. Okay. #T. Yes, that's a quine too. #F. All right, come on. Oh, okay. Well, that looks more interesting. Let's just grab that. Oh, that actually is a quine. Well, that's kind of cool. All right. So what else can we do? Well, we could try. How about we do twines? What's a twine? Twine are two programs that are different from each other, P and Q, such that P evaluates to Q and Q evaluates to P. So how would we do that? Well, we need another variable, right? So we can get a P and Q, okay? And now what? How you doing, Ann? That's a good question. That's the right question. The question, or the answer is we just like put things next to each other. That's one way to do it. Okay, PQ and QP. And we want to make sure that P and Q are different. So I'm going to use this constraint called disquality constraint to say that they're different. So let's see if this actually works. So it might not surprise you that depending on how big the interpreter is, how many clauses there are, this may take longer or may come back faster. So let's see. So we've got this expression that has a quote on it at the front. Let's run it. And we get back, we get back this expression without a quote. Let me try running that. And now the version we get back has a quote. So these really are twines. And you can play these games all day long, okay? All right, so that's cool. That brings us up to kind of the state of the miniKanren relational programming as to, I don't know, 6 months ago or something like that. And then a PhD student at Utah I was working with said, Michael Ballantyne, he said, well, what would happen if you take your fancy relational interpreter and you run scheme append inside of it? I was like, well, that's a good question. Remember all that appendo mucking around we had to do? What happens if we just take append and run it? So let's try that. All right, so let's look in here. All right, so here's our append. Okay, so here is a different version of append. In this version of append, it's really what we wrote before, just the scheme append. The difference is I'm using letrec, which allows me to define recursive functions, okay? So this is just so I don't have to mess around with define, which is like the top level construct. It's a little messy. So I'm going to run that, and sure enough, that works just fine in scheme. It works in racket too, okay? So let's take that whole expression, and let's evaluate that. So I can do a run one Q, and I'm going to do an evaluate of this expression. And I'm going to say the output is Q. Okay. So what should I get back as Q for Q when I do this? A, B, C, D, E, right? It should just append it. Yeah. Okay. All right. So I'm just running it forward. That's cool. Well, what can I do now? Well, let me try this. So I can take the output, A, B, C, D, E, all right? And what I can do is I can put a logic variable inside of the call to append, right? Like I could put a logic variable there, the query variable. So now what should I get back? I get back ABC, okay? So this is kind of cool because we're just taking scheme code now, right? This is not code that was miniKanrenized. We're just running it in the relational interpreter, and we get this ability to run backwards. All right. Is there a second answer? So, what's going to happen if I do like a run star? Is there a second answer to this? Well, let me try a run 2. You know, obviously, ABC is the only answer, right? Oh, what is this? Anything that evaluates the ABC is the right answer because we're in an interpreter now, right? So any expression in scheme or in our interpreter that evaluates the ABC will give us this, okay? All right. Well, that's kind of cool. So let's go back and put back ABC again. That should be consistent. Cool. Where else could we put a logic variable, by the way? The definition of append? Nah. All right, let's put it there. Surely that can't work. Let's see what we get. Hey, yes, that's what I just removed. Huh, is there a second answer? Wait, what is that? miniKanren cheated. All right, so we're going to keep miniKanren from cheating using absento. We'll say, okay, well, better not have a symbol D in the answer, right? See if that works. Hey, there we go. And it's doing a match and then just giving us S back. Okay, so bless his heart. It's not cheating anymore. All right. So we could also do other things. We could try putting the query variable other places. Now, with the current version of miniKanren, the current way we're doing this, we're doing some code synthesis here, some code generation based on the examples, but in order to really make this efficient, we're going to have to use some extra tricks. So that's why last week Michael and I were at a program synthesis summer school, and we're eager to apply a bunch of these techniques to miniKanren. So we can do some of these things. We have the expressive power now to express these sorts of queries to do code synthesis, but we need some additional techniques to make it efficient. All right, so that's kind of cool. That's kind of cool. So let's see what else we could do. All right, so I've got an idea. Let's look at something a little more complicated that we're going to run inside of Scheme. Okay, well here's something. I just happen to have this laying around. This is a this is a proof checker. This is a proof checker. So Matt Might wrote this, and this is a proof checker for propositional logic. So this is where the variables can be true or false, and we have a rule of inference called modus ponens that basically says if we know A is true and we know A implies B, then we can infer from that information that B is also true. Okay, so that's the sort of inference we can do. And Matt, wrote this code just in Scheme basically. He did use a pattern matcher when he wrote this code. He wrote the code originally in Racket. So we've added a pattern matcher that has a subset of the Racket syntax. It doesn't handle all the Racket pattern matching, but it handles some of it. And to show you that I'm not really cheating, let me see if I can pull this off. So let's bring up Racket, and I'm going to try just running this forward. Okay, so this is so I got back hash t. So here I've got like a little simple proof. The thing I'm trying to prove is if I know A and I know A implies B and I know B implies C, we're trying to show that C holds. And this really is a proof checker. It's not anything more than that. And we actually have to give the entire proof tree. And the proof checker is just checking to see if this proof is actually valid. Okay, so it's a proof checker. You have to come up with a proof by hand. So what do you think we can do when we run this in miniKanren? Leave out the proof. What if we put a logic variable where the proof is? Well, let's try it. All right, so first of all, let's just run it forward, make sure that works. Okay, that should give us like a true. Okay? And I did a run star, by the way, so it tried all the possible ways to prove it. Okay, so I get back hash t saying that proof is actually valid. Okay, and now let's take a variant of that code. We didn't change the proof checker code at all, but what we did is we put in a logic variable in the proof itself. Okay, so now we don't actually have the proof tree anymore. We just have what we're trying to prove. Okay, we know that we have some information. We know A, we know A implies B, and so forth, and we know we're trying to prove C, but we don't actually have the tree. So let's see if we can find a proof of this. Hopefully. Okay, and you can see that we actually get back the same proof tree as we had before. So our proof checker is now a theorem prover by running it in the relational interpreter. Now, of course, there's interpretive overhead. That's why it's taking so long. So we should be able to do things like partial evaluation to make this run significantly faster. But you can see that we've increased the expressive power by running these programs inside the relational interpreter. We basically get new features for free. Okay. All right. I think we started a little late, so I'm not sure how much time I have left. There's one other thing I was going to show, but I'm not sure. You got 7 minutes? I got 5 minutes. Okay, that's plenty of time. All right. Okay, so let me show you one more thing that we've played around with recently. So everything I've shown you has basically been expression-based. So we're running in Scheme. We're running in a pure subset of Scheme. And while that's cool and why I like Scheme a lot, there is a question of what can you handle effects? Can you handle things like variable assignment, destructive variable assignment, and mutation? Can you handle things like errors? Or does this only work for a purely functional language? And well, so we started playing around with this while language, and the while language is a little like it's a little like the lambda calculus for imperative programming, if you will. And this is these are some rules, semantics rules from this Nielsen and Nielsen book called Semantics with Applications, which is available online, which is a nice book. And basically, I was able to just type these rules into miniKanren, and I typed in a few other sets of rules. But now we have a little language called while, which is an imperative language. It has a while loop. It has an if statement, not an if expression. It has variable assignment, variable lookup, that sort of thing. And we also added abort, which is like an aborting error message. It stops the computation. Okay? So let me see if I can load that. Okay, cool. All right. And I have some examples here. So an example I wanted to show you is something called symbolic execution. It's an example of symbolic execution. And I've got some, maybe the easiest way to show it is these slides by Stephen Chong from Harvard. He's got some nice slides online. I think Jeff Foster wrote some of these slides also. But he has an example of symbolic execution. So symbolic execution is basically a way of trying to infer the initial values of arguments that are variables that can get you to a certain point in your program. So here we've got a little simple imperative language, which is very similar to the while language that we implemented. And so we've got some integer variables, A, B, and C, coming in, and they are assigned some initial values, alpha, beta, and gamma. And these are constants. We don't know what those constants are, right? And we also have some other variables, x, y, and z. They're also assigned to be 0. And then we have some conditional logic. If A is true, which means basically if A is not 0, then we assign x to be some value. If B is less than 5, then we do some other ifs and things like that. And you can see we've got various assignments. And then we have an assertion at the end. The assertion, if you'll note, involves the value of x, y, and z. So we violate the assertion if x, y, and z sum to 3. X, Y, and Z are involved in the addition. A, B, and C are involved in the control flow. So you'll see that these ifs are all involving the A, B, and C. So what we want to try to do is infer values, the initial values of A, B, and C that would result in violating this assertion. Okay, so what we want to do is infer alpha, beta, and gamma from this. So basically we've taken the code from those slides and we've changed it into our language, our version of while, which is sort of S expression based while. And so here is what the program looks like. I decided not to handle negative numbers because I don't want to. But it doesn't matter for this example. So this is what that program looks like. And let's see if we can actually do inference. So here's the program, and here is the query. And you can see in this query, we are trying to infer alpha, beta, and gamma. Those are the initial values of A, B, and C. And the way we're going to do it is we're going to say that when we run this code, we actually want the abort to happen. The abort is basically our version of the assertion. And if we try it, we get back this answer. So we get some side conditions. But you can see, now this is a strange representation of numbers due to Oleg Kislyak, which we call Oleg numbers in appreciation. So this number is 0, clearly. This number is 4. And this number is, it's any number not 0. Okay, so we're dealing with non-negative integers. So this is some positive int. All right. So that's how you read these numbers. We could also use piano numerals. We could use a finite domain solver, which we have in miniKanren, and make it look all Arabic numeral-like. But it doesn't matter for this purpose. We can infer that. And so basically we're saying that A is 0, B is 4, and C is something that's positive. And sure enough, that's actually the example. That's what you get back for the symbolic execution. So the cool thing to me is that we didn't have to write something. We didn't have to write code to do symbolic execution. We got that for free by running the program in the relational interpreter. So we've seen that you can run programs forward, you can run them backwards, you can run code that's written in Scheme, but even though it's a function definition, treat it as a relation, and by running inside the relational interpreter, we can do some code synthesis. We can certainly express code synthesis. It's not very efficient yet. And we can also express things like symbolic execution. All in the same framework, all using the same approach by basically implementing the rules for the programming languages directly from the semantics and in miniKanren. So anyway, I think this is really interesting. It's really fun to explore. It can be very frustrating. It's not so easy. It took us like a long time to get to this point, right? But it's really, really cool. And now that we have this expressive power, now we're trying to figure out ways to make it more efficient so that we can actually use it. But it's a very general approach, and if you've never done this sort of programming before, it really changes the way you look at programming. So I hope you'll find this interesting and you'll want to learn more. I'll be around for the rest of the time. If you want to learn more about miniKanren also, you can look at the miniKanren.org website, which has lots of information. And also, I do weekly hangouts on Sundays. Well, not this Sunday, but on relational programming in miniKanren. So if anyone's interested in joining us, I've got a bunch of YouTube videos, and we also do weekly live hangouts for people who want to explore this stuff. So I think that's it. So, thank you.
Anyone has some questions? Okay.
42.
Hello, I have a question. Maybe it's silly, but what if your relation isn't recursive?
What if it isn't recursive?
Yeah.
Okay.
I mean, you plug in some stuff that solves unsolvable problems.
Oh, okay. So what happens if you want to solve something that's like not computable or something that yeah, sure. So that's a very good question. miniKanren, although I don't know if you saw my desktop, but so although miniKanren is like very magical, it doesn't have the ability to solve the halting problem quite yet. So basically miniKanren has like kind of two modes, right? So miniKanren has the mode of, hey, you've got an answer, and I'll find it for you, And it might take a trillion years, it might take a millisecond, but if it's there, I'll find it for you. And miniKanren, if there is no answer, miniKanren will either sometimes terminate in finite time, saying as a proof there is no answer, or it could happily go in an infinite loop, and it often does. Okay, so if you want to solve Hilbert's 10th problem, which you can easily express with our number system that I just showed you, then guess what? It might go in an infinite loop, right? Because that's an undecidable problem. So that's a good question. This is something. So I would put it this way: if you want to learn about monads, learn Haskell. If you want to learn about recursion, learn scheme or racket. If you want to learn about infinite loops and divergence and the halting problem, learn miniKanren. Okay, because you're going to run into that stuff all the time.
Yeah, so my next question is there any work that is supposed to differentiate problems which can be solved in miniKanren and which couldn't be, like some, I don't know, usage of type system or something like that?
That's a good question. So for the arithmetic system, for example, Oleg actually came up with proofs of termination in certain cases. So we can prove that our arithmetic terminates. We can prove that our multiplication terminates as long as you have certain conditions that you hold. But if you start combining those and you can express Diophantine equations, then we know it's undecidable, for example. So one way you can do is you can actually try to prove properties. Another thing you can do is, like you said, you could try to put some restriction on the system that's going to force it to terminate. So you could try using a type system, will terminate. Or you could do something like put a bound on the search depth, because this is all search-based or has a special solver behind the scenes. So you could do things like that to cut off the search, do incremental deepening down to a certain depth of things like that. And there are other techniques you can use. In fact, there's a variant of logic programming, of Prolog-style logic programming, that is decidable. All your queries are going to terminate, and that's called data log. And if you haven't seen that, it's sort of like a more powerful version of SQL, and that's a very, very powerful approach to doing database programming. So if you're interested in databases, you should definitely check out data log. And the whole point of data log is that your queries terminate, and you get good performance guarantees. Okay, so you can also restrict the logic, and that's basically what you do in data log.
Any more questions?
Is there some particular search policy for these answers, or is it like backtracking like in Prolog?
The question is there any particular search policy, or is it like backtracking like in Prolog? We don't use backtracking. It's all stream-based. The difference between our search and the default Prolog search is Prolog uses what's called depth-first search. That is an incomplete search, meaning that there may be answers that exist that you don't find because your program goes in an infinite loop. In miniKanren, we use a complete interleaving search that has different trade-offs. If an answer exists, we guarantee you'll find it. I mean, it might take a trillion years, it might take, a little bit of storage. But in theory, it would work. However, there's a trade-off in terms of efficiency, in terms of memory usage, for example, right? But we want to make sure that our system will find an answer if it does exist. And that also means that we have certain properties, like we can reorder the code any way we want. And if an answer exists, doesn't matter. We can reorder all the conjuncts and the disjuncts. miniKanren, you can sit there and transpose the expressions all day long, and you still have the same semantics. So that's a really neat property. There's a caveat. If your program has no answer, if that query has no answer, it might go in an infinite loop with one ordering and not go into an infinite loop with another ordering. But if an answer exists, it doesn't matter what the ordering is in terms of the meaning of the program.